What if copper, one of the most widely used metals in electronics, could finally become stronger, more heat-resistant, and still keep its high conductivity? Scientists in China say they've just solved a problem engineers have struggled with for decades. In a major breakthrough, they've developed a new type of copper foil. This innovation may change the future of electronics and energy storage. The research team, led by Lu Lei, has introduced a material that balances three critical properties: strength, electrical conductivity, and thermal stability. Traditionally, improving one of these properties would weaken the others. That trade-off was a major limitation. Copper foil is widely used in integrated circuits and lithium-ion batteries. But pure copper is naturally soft and lacks mechanical strength for high-performance environments. Engineers have tried adding other elements to strengthen it, but that usually reduces electrical efficiency. This new study takes a completely different approach. Instead of changing the chemical composition heavily, the researchers engineered the internal structure of copper at the nanoscale. They created what they call a gradient nano-domain architecture. This was achieved using a scalable electrodeposition process. They introduced trace organic additives that guided the formation of ultra-small structural regions, each just about 3 nanometers in size. These tiny domains are evenly distributed throughout the foil. Think of it like reinforcing a soft metal with invisible microscopic rivets. These nanodomains block the movement of copper grains, making the material much stronger while still allowing electrons to flow almost freely. The results are impressive. The new copper foil reaches a tensile strength of around 900 megapascals, significantly higher than conventional copper. At the same time, it maintains about 90% of pure copper's electrical conductivity, far better than most high-strength copper alloys. It also shows strong resistance to heat, making it more stable under demanding operating conditions. This is key for next-gen energy systems. Perhaps most importantly, the researchers say this method is already compatible with industrial-scale production. It's not just a lab experiment. This has real potential for manufacturing in electronics and next-generation energy systems. It challenges a long-standing materials science limitation. Normally, when metals are strengthened, electron movement becomes more restricted. This approach strengthens copper without disrupting its purity. Instead of relying on chemical changes, it uses nanoscale structural control, essentially redesigning how atoms are arranged. This could improve everything from smartphone chips to electric vehicle batteries and high-performance computing systems. It could also reduce overheating issues and improve durability in compact electronic devices. But real-world challenges remain. Long-term reliability and mass production consistency will determine whether this material becomes widely adopted or stays specialized. In my view, this is a strong example of where materials science is heading. It's about controlling structure at extremely small scales. If industrial production claims hold true, this could quietly become a foundational technology powering the next generation of electronics. But the real test is whether industries can adopt it at scale without sacrificing cost and reliability. That's where many materials struggle. Still, this is definitely a promising step forward in bridging performance gaps in modern electronic systems. The future looks bright and conductive. As we push the boundaries of what's possible, it's often the smallest changes at the nanoscale that make the biggest impact globally. From the chips in our pockets to the batteries in our cars, the evolution of materials continues to redefine our world. Stay tuned for more updates on the breakthroughs that are building our future, one atom at a time. I'm your news explainer, bringing you the latest in science and technology. Thanks for watching.